sensitive enough to measure that small reduction in starlight and thereby detect the presence of the planet. Launched in 2009, the Kepler spacecraft spent more than 4 years continually watching 150,000 stars, 24 hours a day, 7 days a week, 365 days a year, looking for any slight dimming in those stars that might be the tiny telltale sign of a planet. By analyzing the resulting data, Kepler scientists have so far identified about 4,700 exoplanet candidates and have validated about 1,000 of them as confirmed exoplanets. Today's announcement adds dramatically to the number of confirmed exoplanets discovered by the Kepler Space Telescope. Here to make today's announcement is Tim Morton of Princeton University.
All right, thanks, Paul. So today we are announcing the discovery of 1,284 new planets from the Kepler mission. So this is the most exoplanets that have ever been announced at one time. As you can see in Figure 2, Kepler has been leading in the discovery of planets outside our solar system. And this announcement, which is represented by the orange bar, more than doubles the number of known Kepler exoplanets. When Kepler first detects a signal like what Paul showed just a minute ago, we initially call it a planet candidate. That's a term that Paul also used. The reason for this is that there are other scenarios that can mimic the signal of a transiting planet. Figure 3 illustrates 3 examples of these imposter scenarios, or different ways in which companion stars can masquerade as planets.
I just went live. If you guys can hear me, let me know in the chat.
In the top left panel of Figure 3 is illustrated a planet passing in front of a star, and the other 3 panels illustrate different configurations of stars that can cause planet-like signals in Kepler data. So because of the potential for these false positives to impersonate planets,
notice that everything's labeled wrong here.
Verifying a candidate as a true planet has traditionally involved detailed, in-depth study on a case-by-case basis using follow-up observations from ground-based telescopes. Figure 4 illustrates examples of the kind of follow-up observations that are typically done. These might be radial velocity observations to determine a planet's mass, such observations to rule out the existence of imposter scenarios, such as with Kepler 186f and many others. So one of the biggest challenges for Kepler is that these follow-up observations that have been traditionally used to verify planets are time and resource intensive. Figure 5 shows the size and host star brightnesses of both transiting planets found in ground-based surveys and Kepler candidates. It's taken about 15 years of hard work for astronomers to find and confirm about 200 transiting planets that have been found from the ground. By contrast, there are over 4,000 Kepler candidates, and these are overwhelmingly much smaller planets and around fainter stars than most of the planets that have been confirmed from the ground. So a good analogy here is to imagine planet candidates as breadcrumbs. So if you drop a few large pieces of bread on the ground, you can pick them up individually one by one. This is like the ground-based transiting planets. But if you spill a whole bucket full of small crumbs, you're going to need a broom to clean them up. So our broom here is a new analysis technique that enables us to quantify the probability that any given signal is in fact caused by a planet without requiring any follow-up observations. Figure 6 illustrates the 2 ingredients that go into this calculation, which are 2 different kinds of simulation. First, we simulate the detailed shapes of the signals caused by both planets and imposters. This is illustrated in the left panel of Figure 6. And then also we simulate how common we expect imposters to be in the galaxy. This is represented by the dice. Combining these two different kinds of information gives us a reliability score between 0 and 1 for each candidate. And candidates with reliability greater than 99% we call validated planets. Figure 7 summarizes the results of these calculations and shows where these new planets we're announcing today come from calculating this imposter probability for every Kepler candidate. The whole pie here represents all of the signals that Kepler has classified as planet candidates in their latest catalog. Nearly 1,000 of these, this is the blue slice, have already been verified as planets, and 1,284, the orange slice, are the candidates which we have newly identified as being more than 99% reliable and that we're announcing today as new planets. The two other slices in grayscale are candidates that we've determined to have less than 99% reliability. But as you can see, the majority of these are still more likely to be planets than they are to be false positives. That's the dark gray, even though we can at this time claim validation for these candidates. So again, today we're announcing over 1,200 new Kepler planets. Figure 8 shows these new discoveries broken down by planet size. The blue bars represent the planets that were known before today's announcement. This is the planets with known sizes that were known before today's announcement. And the orange bars are the new planets that we're announcing today. So as you can see, we have more than doubled the number of known exoplanets, smaller than the size of Neptune. And this includes over 100 new planets smaller than 1.2 times the size of Earth. These are planets that are almost certainly rocky in nature. So with that, I'll hand it over to Natalie Battaglia, Kepler's mission scientist at NASA Ames, and she will give some broader perspective.
Thanks, Tim. Yeah, I'd like to say a little bit about how we got here and how this work fits into Kepler's broader goals, namely to determine the fraction of stars that harbor potentially habitable Earth-sized planets. Before there was a Kepler spacecraft, there were teams building ground-based precursors or test beds to demonstrate that transit photometry, which Paul described in slide 1 in this first figure, is a viable method for detecting planets. And we were among those teams. We built a small robotic telescope in an abandoned dome on top of Mount Hamilton, here just east of Silicon Valley. And we have started observing the same part of the sky that Kepler ended up looking at for 4 years. And in those early years, we were really plagued by false alarms, signals that looked like transiting planets but were later deemed imposters. We could count on throwing away 60 to 70% of the transit-like signals that the telescope recorded. But now fast forward to 2009, Kepler launches, looks at its first few months of data, and finds right out the gate hundreds of transit signals. But we were cautious. We were prepared to have to throw away 60 to 70% of the candidates like we did with our ground-based surveys. Tim was the first person to critically examine that assumption. He asked the question, how many confounding sources should we expect to see, given what we know about the galaxy and given the quality of the Kepler data? And so a couple years after launch, he told us a surprising thing. He told us to expect that about 90% of Kepler's candidates are likely to be real planets. Indeed, if you add up the numbers in Tim's pie chart, you'll see that only about 16% have a larger than 50-50 likelihood of being an imposter. So in the ensuing years, Tim took his methods to the next level, providing us, as he said, with a probability for every single signal teased out of the data, the probability that that signal is due to an astrophysical imposter. So why is this important? Yes, it gives us a catalog of 1,284 new planet validations. But for Kepler, it's much, much more. Kepler is interested in statistics. We are sampling the galaxy to understand how many planets there are and how far out we have to search in order to find potentially habitable planets like Earth. So far, to date, we have found over 4,500 planet candidates, and now the task at hand is to transform that discovery population into the actual population of planets that's in the galaxy. So in Figure 9, we see the footprint of the Kepler detectors projected against the sky, marking a swath of space that Kepler combed for planets during its prime mission between 2009 and 2013. So let's imagine that the yellow points you're seeing represent the stars with planet candidates. Well, for every one that we see, we know that there are 10, 100, even 200 others out there in the galaxy that we didn't see simply because the planetary orbits are not lined up in that eclipse geometry that you saw in Figure 1 in order to know what the actual planet population is like. We also know that some fraction of these are going to be imposters. Now, they say not to count your chickens before they're hatched, but 10's numbers allow us to do exactly that. For example, if 10 of these candidates represented by the yellow dots have only a 50-50 chance of being a planet, well, we would consider only 5 discoveries representing that population. This is going to be very important for Kepler's most valuable planet discoveries, those small planets orbiting in the habitable zone. So in Figure 10, we are showing that valuable population. We're showing Kepler's Goldilocks or habitable zone planets, those that are smaller than twice the size of Earth. So I'm showing them here in a scatter plot, where the temperature of the star, the host star that the planet's orbiting, is on the y-axis, and the amount of energy received by the planet at its average orbital distance is plotted on the x-axis. So you would have cold, distant planets on the right-hand side of the diagram and the warmer planets orbiting closer to their host stars on the left side of the diagram. The temperature of our own sun is about 5,800 degrees Kelvin, so it would be represented by the largest star symbol on the left, and you can see the solar system planets, Venus, Earth, and Mars there, lined up on a horizontal line at that temperature. Let's see. The sizes of the symbol, I should add, are proportional to the size of the Earth. So that gives you an idea of how big the planets are. And then that green shaded region, the region that's bracketed mostly by Venus and Mars, is the purported habitable zone, where water could potentially pool on the surface of a planet. So over the years, Kepler's identified a few dozen small planet candidates in the habitable zone. In this graphic, we include only those that have been verified. A dozen were verified in past efforts, and those are colored with blue symbols. Some notables you might remember are Kepler 186f in the bottom right-hand corner, Kepler 452 in the upper left-hand corner. And now Tim's work has added 9 more planets to this exoplanet Hall of Fame, if you will. These 9 planets are represented by the orange spheres in the figure. Now, as Tim pointed out, the advantage of this validation technique is that it does not require extensive follow-up observations. Remember, it's the broom that has swept up the largest pile of validated planets ever to be announced in one discovery paper. But the absence of those follow-up observations also implies that there's room for improvement. It's hoped that astronomers around the world will point their telescopes at these systems to better understand the properties of their host stars and the properties of the planets themselves. And as that happens, the orange points might move around slightly in this diagram, but that does not negate the fact that these are with greater than 99% likelihood planets. So we shouldn't overinterpret this diagram and take the positions of these points as literal truths. As I said, they will move around slightly. That said, I'm especially intrigued by Kepler 1229b, for example, in the lower right-hand corner, the orange sphere next to Kepler 186f. That's actually, it's Earth size, but closer to the middle of the habitable zone, so it's scooched over there a little bit to the left. I'm also intrigued by Kepler 1638b in the upper left-hand part of the diagram, sitting up there next to Kepler 452b, also about 60% larger than the Earth, and orbiting a star that seems to be slightly warmer than our own sun. So Kepler's prime mission has entered its closeout phase. We have until October of next year to produce our final discovery catalog and to quantify these scaling factors that will allow us to transform the discovery population into the actual population of planets in the galaxy. And we're working hard to leave an archive of data and measurements that will be a lasting legacy to the science community. Mostly we're getting ready to pass the baton to future missions. And so I will conclude by saying that this new methodology that Tim has described will be directly applicable to future exoplanet finders, missions like TESS, which will launch in 2017, and the European mission Plato, which will launch in the 2020s. As you've seen, it will also help us to determine the fraction of stars harboring potentially habitable Earth-sized planets, a number which is especially relevant to the future of our search for evidence of life beyond Earth. So with that, I will hand it off to Paul Hertz, the director of NASA's Astrophysics Division, who would tell us more about that future.
Thank you very much, Natalie. So as I said earlier, the Kepler Space Telescope is the first telescope capable of detecting small rocky planets in the habitable zones of their parent stars. When NASA decided to build and launch the Kepler Space Telescope, we did not know if exoplanets, especially small rocky exoplanets, were common or rare in the galaxy. Thanks to Kepler, and thanks to scientists like Tim and Natalie and their colleagues, we now know that exoplanets are common, that most stars in our galaxy have planetary systems, and that a reasonable fraction of the stars in our galaxy have potentially habitable planets, that is, rocky planets in the habitable or Goldilocks zone. Knowing this is the first step to addressing the question, are we alone in the universe? Figure number 11 indicates NASA's strategic plan towards answering that question. In late 2017, NASA will launch its next exoplanet mission, the Transiting Exoplanet Survey Satellite, or TESS, which Natalie just mentioned. TESS is going to use the transit method, just like Kepler, and survey the entire sky, discovering transiting exoplanets around the nearest and brightest stars. These are the best targets for further study because they're close and because their stars are bright as seen from the Earth. The statistical techniques that Tim has reported today will be an important tool in interpreting the TESS observations. In October 2018, NASA will launch the James Webb Space Telescope. The Webb telescope will be capable of observing transiting large exoplanets and detecting starlight from the parent star as it filters through the planet's atmosphere. By studying that filtered starlight, scientists will start to understand the atmospheric composition of those large exoplanets. The ultimate goal of our search is to detect the light from a habitable exoplanet and analyze that light for gases like water vapor, oxygen, methane, and carbon dioxide, gases that might indicate the presence of a biological ecosystem on that planet. NASA has just begun developing the Wide Field Infrared Survey Telescope, or WFIRST, which will launch in the mid-2020s. WFIRST will have a coronagraph, which is a camera capable of blocking out the light from the parent star and letting the light from the exoplanet through to the detector. The WFIRST coronagraph will be the first camera capable of imaging planets as small as Neptune that are as close to their star as Jupiter is to our sun. But the ultimate goal is to image planets that are as small as the Earth and are as close to their star as the Earth is to our sun. The knowledge we learn from TESS, the Webb telescope, and WFIRST will enable us to plan such a large space telescope in the future. So as we proceed with building TESS and the Webb telescope and WFIRST, the Kepler Space Telescope continues its studies of the solar system and beyond. Here, to provide an update on Kepler's ongoing mission, is the Kepler and K2 mission manager, Charlie Sobek at NASA's Ames Research Center.
Thank you, Paul. I wanted to just finish up with a few comments on the perspective of the mission from where I'm sitting. Kepler has took observations for a period of 4 years at one part of the sky, and has produced a singular and remarkable data set, which we're seeing the continued investigation of, the continued mining of data within that data set. As Tim showed, even 3 years since we made our last Kepler observation, he's coming up with this 1,200 plus new planet verifications. And I think that people are going to be looking at our data set for years and years to come, doing this kind of work and further discoveries. And then, as Natalie has pointed out, Tim is also providing these probability estimates for each and every one of these detections. And that is going to lead to population studies where we can study the demographics of planets within the galaxy. So I'm really pleased to have been working on the Kepler mission and seeing these kind of outputs. The mission itself will close out, as Natalie said, in another year and a half or so, and we'll finish our analyses, and we'll leave it to the rest of the science community to continue that work. In the meantime, the Kepler spacecraft continues to operate as the K2 mission, extending that legacy to additional new fields of view within the ecliptic plane, looking at new areas of science, opening the door to new areas of science. We're able to see things that we've not been able to see with Kepler. We're seeing things within our solar system and beyond, even other galaxies where we see supernova and active galactic nuclei. Together, the Kepler and K2 missions are part of this, what I think of as an arc of discovery, which does extend from the work that has been done from previous telescopes like Hubble onto what these new missions are going to do, as Paul has described. It's been a privilege working on Kepler, and it's really fun to see it continue doing this work.
Thanks, Charlie. And with that, we'll start the question and answer session. We have several reporters on the telephone bridge today, so we'll need to limit everyone to one question and one follow-up. Once everyone has had a chance to ask a question, and if time permits, we'll start from the beginning again. Our operator should identify you, but if not, please identify yourself, your media affiliation, and then direct your question to a specific panelist if possible. For those dialing in, push the *1 keys on your telephone to be placed in the queue. To use
Did
Twitter,
the sound go out?
please send your questions to hashtag
Can you guys let me know
#NASA.
in the
And
chat?
with that, we'll start with the first. Let's start with Reuters.
It's Irene Klotz. I have a question probably for Tim. Is it correct to interpret this 1,284 planets as going off of the candidate list and onto the confirmed list, or is this in addition to some numbers? And if you have the overall tallies now, that'd be helpful. And I do have a follow-up. Thanks.
Yeah, that's correct. So this population of 1,284, if you refer to Figure 7, the pie chart there, we're going to be, those 1,284 are added on top of the previously confirmed validated system. This is they are moving from candidate status to confirmed status. Now the exact numbers, so the Figure 7, again, it refers to the results from a particular catalog. So this 984 number, that's the blue slice, does not include some confirmed Kepler planets that did happen to not be in that catalog, such as circumbinary planets and a few others. So the total number of confirmed planets is slightly different from the sum of 984 and 1284, but I think that number is on Figure 8, which is the 2,325 is now the total confirmed planet count from Kepler.
Thanks. And the other thing I was wondering about is if the certainty of greater than 99%, how does that compare with the certainty that is achieved with the 200 or so planets that were followed up with ground-based observations? In other words, can you just compare a little bit about what the statistical technique shows versus what the physical observational techniques achieve?
That's right. Yeah, thank you. So that's a great question. The 200 or so, almost all of those planets that have been found from the ground had radial velocity confirmation of their masses. So that's a much stronger verification of the planet status than a 99% probabilistic calculation, which is what today's discovery is. Although I would say that 99% is just a cutoff. So there are some planets that are close to that threshold, but then there are some that are 99.999% likely to be planets in validated sample from today. And another thing, just to follow up on that, is there is a small subsample of the candidates that I've done my calculations on and that have also been followed up from the ground in various studies. And the identification of false positives and true planets that came from the ground matches up very well with the probabilistic calculations that I've done here. So again, the ground-based, whenever it's possible to measure NASA's rate of velocities, that's the best thing you can do, but that's just not possible for the vast majority of Kepler candidates.
Okay, next question. We have Peter King from CBS News.
Great, thank you, and good afternoon, and congratulations. I think this question is for Natalie Battaglia. First of all, I want to know that I'm saying your last name right. Is that a correct pronunciation?
And then maybe
it was very close, Battaglia. Thanks for asking.
Well, that's important for us in radio. And here's the question is simply this. You were talking about the Goldilocks planets, and I'm just curious if you've got a tally or an estimate of how many Goldilocks planets you've found, and I'm wondering how close would be the closest of them to us?
Yeah, that's a great question. Exactly the kind of thing that Kepler is designed to do. So Kepler has detected about 36 planets or planet candidates in this Goldilocks zone. So what you're looking at in Figure 10 is about 24, about 21 are represented here. There are another dozen or so candidates that have not yet been verified, and those candidates tend to be associated with the warmer stars, like maybe from 4,500 Kelvin up to 6,500 Kelvin. And so we're still looking at those and scrutinizing them. So let's see. The second part of your question is how many, what does this imply about the population of small, potentially habitable planets out in the galaxy? There have been some studies to date, mostly associated with those cool, lower mass red stars that you see at the bottom of Figure 10. Towards the bottom. That's a nice sample for doing demographic studies, and that sample implies that about 24% of the stars harbor potentially habitable planets that are smaller than about 1.6 times the size of the Earth, a number that we like because it's below that size that we think planets are most likely.
I think I had enough here.
So if you take that estimate
so basically,
and
the story here is that they're announcing
that there are more than 10 billion such planets in our galaxy alone.
1,280-something exoplanets.
If you ask yourself the question, where
they
is
admitted
the
in the talk that
potentially
they're
habitable
basically,
planet likely to be, you find that it's going to be within
did a
about
sweep
11
of the
light
planets,
years,
and then
which, astronomically
this is the
speaking,
data that's coming
very
through.
Close. That's a very close
and
number.
they've only done one sweep or whatever. I don't know. What do you guys think? Do you guys think this is just all hogwash? Because in my opinion, there's just no way to verify any of this stuff. It's just data that a scanner collected, So I'm going to read in your chat here. I know the chat's a little bit behind of the actual live thing, but
we have Tufts Quidditch asking, how do you plan on studying these new planets more in depth? Surface conditions, chemical composition, etc., and classify planets. And the other question is, are there any new Kepler exoplanets free-floating? Are there any new systems with 7 planets or more?
Yeah, one sec. I just totally clicked out of the channel to get the chat.
Well, let's see. Strategically, I'll start with the strategic question. How do we plan on following these up? Kepler is a statistical mission. Our primary goal is to determine the statistics of planets in the galaxy orbiting within kind of an Earth orbit and inward. So we're really probing the inner regions of planetary systems. So Kepler's goal is not necessarily to do the kinds of things that you're talking about. Now, future missions, of course, are going to do that. We mentioned the TESS, the dynamic duo, which is TESS plus JWST. TESS is going to find the nearby transiting planets by doing a whole sky survey, and then JWST will be able to look at the starlight that's filtering through the atmospheres to try and understand the diversity of atmospheres orbiting those, associated with those planets. So I don't know. I think over the next decades, people will use ground-based telescopes and other space-based telescopes to follow up Kepler candidates. I think we'll see that JWST will also characterize some of the Kepler and K2 planets. But that is not our primary science objective. So I don't know. We'll see how it plays out. And then your second question, maybe Tim, would you like to take a shot at the second question?
Sure. If I remember correctly, the question was about, are there any new 6, 7 planet systems or something like that? I'd say that most of the largest bounty single systems that Kepler has found many of those have already been verified as planets in previous. So the last large announcement of Kepler planets was a large announcement of planets that were in multiple planet systems, and that contained much of the news about the large numbers of planets in a single system. So I think this announcement, it probably does, it definitely does add to the number of planets that are known securely in multiple planet systems, but there aren't any, as far as I know, there aren't any specifically dramatic, 6 or 7 planet systems that are new in this announcement.
Okay, now we have Tracy Watson from USA Today.
Thanks. For Dr. Battaglia, can you do the math for me on Figure 10 and talk about how many of those planets might be, those new habitable zone planets might be rocky, and which maybe are the most likely to stay where they are on that habitable zone plot? And then I have a follow-up. Thanks.
Well, let's see. So our understanding of what constitutes a rocky planet is changing with time. Our best guess currently is that planets smaller than about 1.6 times the size of the Earth are more likely to be rocky. So if you look, for example, in the upper left-hand corner, Kepler 1, that planet is kind of on that border. So the symbol sizes are relative to the size of the Earth. So any ball on this graphic that's that size or smaller is in that size range. Now, when I quoted the statistics earlier, this kind of 25% ballpark number, that is excluding all the planets that are bigger. So that's only considering the ones that are smaller than 1.6 Earth radius. So you might look at this graphic and you say, wow, there's really not that many planets that are smaller than that size cutoff. And that's true. These are the hardest planets to find, right? So these are the select few. This is the Exoplanet Hall of Fame. These are the things that are really hard to find. And we do suffer from small sample statistics. Nevertheless, we can take these discoveries and we can transform them into that population, a value that we call Eta Earth, for example, which is the occurrence of small planets or potentially habitable planets that are Earth-size, and by that we mean kind of 1.6 Earth radius and smaller. So I'm not sure if I exactly answered your question, but that's would be my response.
Okay, thanks. I'll take another look at Figure 10. But in the meantime, can you also talk about how much of the catalog you still have to go through, how much of the Kepler catalog do you still have to go through, and when you expect to be done going through it using these new methods to either confirm or rule out your remaining candidates?
Yeah, I should say that that's really not my objective in a literal sense. I personally am not that, it's great that we have these new validations, right? We love to say this is, greater than 99% likelihood of being an actual planet. That's really wonderful for the people who do the follow-up observations from the ground and want to study each individual system and understand their characteristics. For statistics, what I really care about are the probabilities. And Tim has already calculated, or in this paper, there are these calculations for every single planet that Kepler has found so far. We do have one more catalog effort that's pending. We've already started that effort. And we expect that to be wrapped up sometime next year as we head towards that mission closeout date. That's at the end of September. But the analysis that's being done is with our most sophisticated software pipeline that detects planets and weeds out the false positives, etc. But it's operating on data that we've already looked at once. So this last catalog that Tim was talking about, what he called the DR24 catalog, that was also looking at Kepler's entire 4 years of data. So it's kind of hard to predict exactly what we're going to see with this new, well-tuned pipeline, but it would not surprise me if we still have some hundreds of new planet candidates to add to that roster.
And just to follow, I'm sorry, go ahead, Natalie.
No, that's fine. Please, Tim, go ahead.
Yeah, so I was just going to add to this. So, again, as far as the analysis that I've described today, that analysis has been applied to all of the candidates that we know about right now from Kepler. Now, one thing to point out, and again, this is illustrated in Figure 7. Another thing to point out here, though, is that there has been, so I mentioned that this particular analysis does not fold in any follow-up observations that have been done on Kepler candidates. However, there have been lots and lots of follow-up observations. A large effort has been ongoing over the last 4 or 5 years to follow up these candidates with telescopes from the ground. And there's been a lot of work that has not yet been folded into these calculations. So in addition to the one final pipeline candidate search that Kepler is going to be doing soon, we will also have the opportunity to fold in the results of all of the follow-up observations that have been done. And this is something that the software I've developed is able to do, but we just didn't do that for this particular effort. Here we were focusing on what can we say before accounting for any of the follow-up observations, then what we're going to do over the next year or so is start to fold in the results of the follow-up observations that have been done. So that will be eating away at these gray pie chart slices.
Yeah, Tim alluded to something that actually addresses a question that I forgot to answer. Somebody asked, how firm are these properties? Like, how much can they move in this diagram? There actually is a public repository of follow-up observation data that's available at the NASA Exoplanet Archive. That information has not been used for this particular study. That doesn't mean that we haven't taken a peek at what that data is telling us, and I've looked at it, I've scrutinized it for all of the candidates that are represented in this diagram, and I really haven't seen any showstoppers. So I don't expect that these points are going to move around a lot. Something might get tossed to the inner edge of the habitable zone, maybe just beyond, kind of like Venus is up there, but I don't think that they're going to move drastically.
Okay, thanks. Next we have Eric Berger from Ars Technica.
Hello, thank you very much for having this call. I had a question for Natalie. You mentioned a couple of the exoplanets you were interested in, Kepler 1229b and Kepler 1638b. I'm wondering if any of the planets on Figure 10, including those two, are close enough that we might get any meaningful information about them from James Webb or from the large ground-based observatories hopefully coming online next decade, like the GMT or the EELT?
Yeah, unfortunately, no. None of them pop out as something that we might be able to characterize with JWST. That said, we do have some very interesting candidates coming out of K2. K2-3, for example, has a slightly bigger planet. It's kind of a little above twice the size of Earth. And there are some very compelling simulations that that are telling us that might be reachable by JWST. So Kepler, or K2, is doing a great job kind of bridging the gap between Kepler and TESS in terms of providing targets for JWST in the future.
That guy asking the questions microphone is super loud.
Okay, now we're going to go to social media, and just a reminder for those that are asking questions via social media to use the hashtag AskNASA. This question is for Natalie. This is from Team Burma. If you were to make an educated guess based on initial numbers, how many Earth-like or habitable planets are in our galaxy?
Oh, goodness. Okay, let's see. Well, I've said that the result for the M-type stars is turning out to be about 25%. We've got some kind of sneak peek calculations that suggest that it might be the same for the warmer stars, the Ks and the Gs. So let's see. There's about 100 billion stars in our galaxy, let's say. Let's say roughly, let's be conservative, let's say 70% of those are kind of main sequence stars. And then, if you take 25% of those and you assume that they are small, potentially habitable planets, you can see, doing the math, that you're talking about tens of billions of potentially habitable Earth-sized planets out there in the galaxy. So that's kind of my back-of-the-envelope calculation. We want to know what the statistics are telling us for the K-type and G-type stars, kind of the orange ball and the yellow ball on Figure 10. Unfortunately, our previous catalogs are not the ideal catalogs for doing those kinds of statistics. It works well for the red M-type stars, but not so well for the Ks and the Gs necessarily. The catalog that we're working on right now, though, is very well tuned for these kinds of statistical analyses. So by time mission closeout arrives, we will have in the public archive everything that we need in order to do those very important calculations for future missions.
Okay. Next question from social media. This is from Evan Petkow. Aren't there more factors involved for habitable planets than temperature and size? What about radiation and atmosphere?
Oh my gosh, absolutely, yes. What Kepler is doing is measuring Goldilocks zone planets. So this is the, fraction of stars that harbor potentially habitable, and by that I mean planets in the habitable zone. So all we're looking at right now, all Kepler can measure, is the orbital period and the size, the radius of the planet. And now the orbital period is related to the separation between the planet and the star. So we can say, okay, how much energy is that planet receiving at that distance, and would that preclude the existence of liquid water to pool on the surface of that planet? And so naive kind of early climate model calculations, simulations, taking an Earth-sized planet and kind of modeling what might happen to it if you move it around, if you put it closer or further away from a star, gives us an idea of what that Goldilocks zone might be. But the boundaries are fuzzy, and yes, indeed, going forward, we want to transform our understanding from habitable zone planets to truly habitable environments and then one day living worlds. So that's kind of the natural progression as we search for evidence of life beyond Earth.
And now we have two more questions from social media. These two are about TESS. I'm going to direct them to Paul Hertz. This one is from TrashNap. What will be the main difference between the Kepler mission and the TESS mission? And from QA Bob, will TESS be capable of detecting planets that don't have a light source behind it from Earth's view?
Thanks, Felicia. Those are good questions. The main difference between Kepler and TESS is that Kepler was looking at one spot in the sky for 4 years. And so it got a 4-year look at 150,000 stars. TESS will look at the entire sky, the brightest and closest stars everywhere in the sky, and we'll look at each of them for about 30 days. So Kepler looked at further away stars, but for longer periods of time. TESS is looking at closer stars, but for shorter periods of time. But because TESS operates with the transit method, the same as the Kepler mission does, it can only see planets if they pass in front of their parent star. So no, TESS cannot detect planets that don't have a light source behind them.
Thanks, Paul. Now we're going back to the phone lines. Next we have Maddie Stone from Gizmodo.
Hey, thanks for having this press briefing and taking my question. So I think this came up in some capacity earlier, but I just wanted to confirm about the K2 mission. I know that all of these planets that are being announced today are from the primary Kepler mission catalog, but I wanted to confirm how many planets have been discovered by the K2 mission, and I was curious to hear a little bit about how they compare in terms of their size and the types of stars they orbit to the ones in the primary Kepler catalog?
I don't have that number off the top of my head, but I think it's a few dozen that have been confirmed. And then I think that there are a couple of hundred candidates that have already been announced. So astronomers are looking carefully at those candidates. I'm sure the numbers are going to change quickly.
Yeah, So I can speak a little bit to that. I don't have the exact numbers, but you can get a sense for the kinds of planets that they are by looking at Figure 5. Again, going back to looking at the size of planets versus brightness, K2 is primarily focusing on stars that are a little bit brighter than the Kepler.
Okay, I wanted to share this with you guys. This is kind of the same stuff. They're just going to drone on here, but one of the most interesting things that they said here so far was they had this diagram up, which is basically
so what that means is
I gotta move
some of these
private conversations here. Okay, so this guy, one of the guys that was talking, put up this image here, which is the exoplanet missions thing. He talked about Kepler, and he's talking about TESS and the JWST, AFTA, and then you have the New Worlds telescope, and they're supposed to do something with it. But here's what's interesting. This is the 2010 New Horizons paper. I just find it ironic and funny that this document here, the Astro 2010 PPP, blah, 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 the New Worlds Observer, if habitable planets are common, NWO will discover them. If life in the universe is abundant, NWO will find it. I just think it's really ironic that they would use NWO, the New World Order, the acronym for New World Order, for this thing. I just thought it was hysterical. So I'll let you guys get back to the what they're saying here, but I just wanted to share that with you guys.
Changes to the distribution. It looks like super Earths and sub-Neptune sized planets are still by far the most common ones that Kepler's discovered.
Yeah, that's a good question. So there are kind of two different things to keep in mind. One is the planets that we know about, the sort of absolute numbers of planets that we know about of different sizes. And if you look at it in that way, we know about the most planets that are around the super Earth and sub-Neptune size. But if you ask the question, which sizes are actually the most common around their stars, then because as planets get smaller and smaller, they get harder and harder to detect. We have pretty good estimates from statistical calculations that have been done based on the catalogs as they exist, that Earth-sized planets are actually more common than super Earth or sub-Neptune, that the occurrence rate of planets continues to rise towards smaller planets. It's just that the reason that we know about so many more of the planets in these sort of intermediate sizes is because they're easier to detect. But again, just to point out, I think one of the biggest things that Kepler has shown us is that there are lots of these planets that have no analog in our solar system. And this announcement today doesn't really change the distribution of sizes that we see in Kepler. Most of the planets that are confirmed are, following the confirmed planets pretty much follow the distribution of the candidates for the most part, with the exception that the things at the largest size, many of those candidates do turn out to be false positives. That's just because it's easier to mimic a signal of a Jupiter-sized planet than it is to mimic the signal of a super Earth. And there's some more detail about sort of how this works it's on the Princeton homepage too, so you can go look at that for some more details.
Okay, next we have Alexandra Witt from Nature Magazine.
Thank you for taking my question. This is for Tim. There have been sort of other probabilistic methods for trying to screen out false positives and get out which planets are real or not. Can you just talk a little bit about what makes your technique different from some of the earlier ones, and especially how you are able to do so many so quickly?
Yeah, that's a really good question. So my method it's sort of based on the same principles that were pioneered by the methods such as the blender method, which we've heard about before, in previous years. The big difference is that it's a fully automated technique that is able to be applied to all of the candidates. It takes just a few minutes per candidate to do these calculations. So it's very easy to the calculations can be done very quickly. So the biggest difference is that it's fully automated. I guess that's the biggest difference.
Okay, next we have Dana Pleka from Denver Post.
Hi, thank you so much for taking my call and my question. I think this is going to be for Charlie Sobek. I was curious about, well, first of all, I'm a little bit confused as to how much longer you expect K2 mission to continue. I've heard a couple of different possibilities, but I'd also like you to comment on what your thoughts are considering last month's emergency mode that Kepler went through and how that might impact the next several months of its mission.
Sure. People know that we did go through an emergency mode last month, and that can be a scary thing for a spacecraft. You don't know what happened to it. But it looks as though it was a transient event. We don't see that the spacecraft is operating any differently today than it operated before the emergency mode. Emergency mode seemed to have done exactly what it was designed to do. It took the spacecraft to a safe place, regardless of what might have caused it to go there. Right now, I think that everything is looking good with the spacecraft. Of course, we never know when the next event or failure might happen, but we don't see anything in the offing right now. The reaction wheels, which failed and ended the Kepler observations, the two remaining wheels look to be excellent. They're in good health, and the K2 mission is ultimately going to be constrained by fuel. And right now, my estimate is going to be something over 2 more years' worth of fuel. So sometime middle of summer of 2018 is when I think that we may run out.
Okay, next we have David Perlman from the San Francisco Chronicle.
Thank you very much. This is for Natalie, and it's a very provincial question. First of all, does the automatic planet finder on Lake Observatory play any role in this? And second of all, what was the dome where you made your first initial observations before Kepler?
Oh, that's a lovely question. So first, the APF, the Automated Planet Finder up at Lick Observatory, is a robotic telescope doing radial velocity surveys. I do believe that there are a couple of Kepler planets that have been observed with that telescope, and there's a graduate student up at UC Berkeley who's been involved with that work, Lauren Weiss. But not so much the faint targets. The faint targets require big telescopes. The Keck 10-meter telescope has been a workhorse for Doppler surveys of Kepler targets because, as Tim said, they do tend to be fainter. Now, the second part of your question is about the dome that housed our robotic telescope, which, by the way, was called Vulcan. The Vulcan telescope made use of an abandoned dome up on Mount Hamilton called the Crocker Dome. It was a leaky, rusty, tiny little dome, and we really learned a lot in that dome. We really cut our baby teeth on that telescope that was in the Crocker Dome.
Thanks a lot. That's all. Thanks.
You're welcome.
Next question, we have Robert Holtz from the Wall Street Journal.
Yes, thank you very much for taking my question. I would like to follow up on something that you mentioned earlier. You said you were particularly intrigued by Kepler 1638b, and I think it was 1129b. I wonder if you'd expand on why you're so intrigued by those two particular exoplanets in the habitable zone.
People often ask me, which are the planets that are most similar to Earth that have been discovered so far? And I think that it's safe to say that Kepler 186f and Kepler 452b have both held that title. Because they are roughly Earth size. Well, Kepler 186f is almost exactly the size of Earth, orbiting a cooler star in its habitable zone, kind of at the outer edge of the habitable zone. Kepler 452b is unique in that it's orbiting a star almost exactly like our Sun, and it's orbiting at an orbital distance that's almost exactly like Earth, around 380 days, I think it was, if I remember correctly. So it's very similar in that regard, but yet it's bigger. It's 60%. So we don't necessarily have an exact dead ringer for a planet like Earth in terms of its orbit and size, but those two kind of hold that title. So I brought up 1638b and 1229b as examples of others that are very much like Kepler 452 and 186f. I wouldn't say that they're necessarily more Earth-like than those two candidates. They're very similar. So, but as I said, as we do follow-up observations, these points are going to move around a little bit. So who knows what we might learn in the future.
Okay, great. Next we have Marion Kramer from Mashable.
Hey, thanks so much for taking my question. I think this is for Tim. I am just sort of curious. There was a study released not that long ago, I think in December, that suggested that it was about a 50% false positive rate for large exoplanets. And I'm just sort of wondering if you could speak to how your work, now fits into this. Is that sort of what it's looking like for large exoplanets, or is the percentage perhaps different? Thanks.
Yeah, thank you. I'm glad you asked that question. I mentioned briefly before that I've cross-checked my statistical calculations with Kepler candidates that have been followed up from the ground, and so that was an example of a study that did a lot of radial velocity measurements on a number of large exoplanets and identified about half of them to be false positive. And pretty much for every planet that the ground-based surveys predict to be, measure to be a planet, I predict that it should have been a planet. And for everything that they identify as false positive, I predict it should have been a false positive. So it matches up very well with the follow-up observation. So again, back to figure 7, the more likely imposter light gray wedge, many of those are these sort of giant planet candidates. And also, again, just to emphasize, there's no size cut in terms of what becomes a candidate in Kepler. So there are many signals that are 2, 3, 4 times the size of Jupiter that are Kepler candidates because we don't know for sure that they're false positives, but my calculations say they're almost certainly to be false positives, and that's why that false positive rate for the larger candidates is so much higher than for the overall sample.
Okay, next we have Bill Hardwood from CBS News.
Tim, just to follow up on a couple of those same types of questions, the chart where you're showing how you do this technique with, you're modeling signals that you've seen before and then determining which ones could be false positives. The second part of that I'm still a little fuzzy on. In other words, is computing how common imposters are based as an extrapolation of data that was collected when you physically went and looked at planets before and determined that, or is there something else going on? That's the part I don't get. Thanks.
Great. Yes. Thank you for asking that. The second half of the right panel of Figure 6, what this represents is basically taking the knowledge that we have from previous studies of how common are binary stars in the galaxy, and how many stars do we accept? What's the density of stars in a particular direction in the galaxy? So that's the kind of inputs. So these are what we call prior inputs. So these are things that before even looking at the Kepler data, how common do we expect binary stars to be? So it's using that sort of information and folding that in with the details of the signal. So that's what the right-hand panel represents.
Thank you.
Thanks. Next we have Michael Tabb from Quartz.
Hi. Thank you so much for taking my call and question. I think this is for Dr. Hertz. Whenever we have a story like this about the search for life beyond Earth, we get a lot of commenters that are very concerned, and sometimes it's hard to tell if it's just internet fear-mongering or not. But are any of these sort of concerns about what we could find factored into long-term planning for search of life beyond Earth, or like when would they be considered?
So I'm going to have to guess what you mean. Right now, all we are doing is looking and listening for evidence of life beyond Earth. So I don't think that's a reason to raise concern. Does that answer your question?
Yeah. I mean, do you think we have a long way to go before you're actually concerned about actually finding something or excited about finding something?
Well, I think that, so we have two prongs of search for life beyond Earth. We are looking for life in the solar system. Currently, we're exploring Mars for areas of habitability, and soon we'll be looking for evidence of past or present microbial life on Mars. We're studying missions to look for habitability on Europa, moon around Jupiter, and and any other place in the solar system that might be habitable. We're investigating, but astronomically, what we've been talking about is we're looking for planets that might be in the habitable zone of their stars, and then understanding what it would take to look at the light coming from those planets and see if there's any hints in the light that might indicate there is biology going on those planets. That's the path that we are currently on for NASA.
Great. Thank you.
Thank you. Next, we have Monica Young from Sky and Telescope.
That was interesting.
Hi, thanks for taking my call. My initial question was actually answered, but I'm going to ask about Figure 8. There's a dip in the distribution around the sub-Jupiter size, and I was just curious if that was real or not.
Yeah, I can take this. My guess is that it probably is. I think there very likely is could be a dramatic change in, how planets, form between the size of Neptune and the size of Jupiter. And I think the fact that we do see a dip there is real. Now, we don't know exactly what that means yet. There are a lot of people working on that, but I do think that is a real dip.
Okay, great. Now we have Mike.
Although, actually, to follow up, sorry to interrupt, it's a little bit distorted, this graph, because many of the Jupiter-sized planets in blue have been found from ground-based surveys that are much easier to find larger planets. So it's a little bit subtle, but there very well could be a dip.
I see.
Okay, now we have Mike Wall from Space.com.
Oh yeah, hi guys. Thanks for taking my call. This one's for Tim too. I just had a quick question. Do you anticipate there are about 2,000 candidates that are still in limbo? 1,300 probables and those 700 that are probably not real planets. Do you anticipate that they'll always remain in limbo, or do you think you can bring them back into the realm of we actually know what they are with some more advanced kind of analysis techniques?
Yeah, it's a good question. So, again, there's a lot of follow-up observations that have been done from ground-based telescopes, and folding that information in will definitely move towards validating more of the dark gray wedge. It's unlikely that any of the light gray wedge will get validated, but certainly with the application of follow-up observations, we will increase the number of known planets from Kepler.
Let me just add, so we have this new catalog effort that's underway, and it's based on a more well-polished, fine-tuned software pipeline for detecting planets. It could be, since part of the analysis is, how well does the data match the model of a planet versus how well does it match a model of an imposter scenario. So with better data, better precision, better statistical metrics for weeding out some of these false positive scenarios, this method might actually bump a population up into the verified category. So I think that we will repeat these calculations on all of the candidates in the very final catalog, and then we'll see what happens.
Great, thank you.
So we're getting a little ahead of ourselves in terms of time. So what we're going to do is I'm going to have 4 more questions, and then we're going to wrap it up. So next we have Mark from Aviation Week.
Yeah, thanks, Mark Carreau for Aviation Week. And I'm just looking for a clarification. the announcement today involved planets that were in the pre-K2 period, or were some from both? I'm not.
No, that's correct. It's from the Kepler Prime mission.
Okay,
so
thank you.
Yeah.
That's it for me. Thank you.
Okay, next we have John Wentz from Astronomy Magazine.
Yeah, hi. My question is actually, how many of the planets in the new find of the catalog are longer period planets that you were able to kind of pull out with these better refinements?
I can. Let's see. So I am looking right
now. While Tim is digging that up, he's going to get you that number.
Okay.
But while he's digging it up, I will just point out that the probability of finding a planet in the transit geometry decreases as the orbital period increases. So planets in orbital periods are harder to find just because they're not as often transiting. So in every time we show one of these kind of period or radius versus orbital period diagrams with the Kepler discoveries, the ranks start to thin as you go to longer period objects. So you expect fewer of them just for that reason alone. But that said, I know that, go ahead, Tim.
So there are 84 greater than 100 days. So that's an idea of gives an idea of the numbers.
Okay, and I guess just a brief follow-up. What is the longest orbital period you found in the data?
Okay, so one of the things that
we have a wall at 700 days, right? Just because Kepler only observed for 4 years.
Yeah, of course. With the length of the observation time, that kind of cuts down on how long you can get. But
that's right, because Kepler requires 3 transits to claim a detection, but the largest in this sample has a period of about 510 days.
Okay, great. Thank you.
Okay, next we have Mark Kaufman from Mini World Space.
Yes, hi. My specific questions were asked and answered. But here's a more general one, and I'm glad to ask this at the very end. The exoplanet era has been nothing if not surprising in terms of people expecting certain things to be found and then they're not found. Was there anything in this new addition and in analyzing these planets that was particularly surprising to you? And this is, I guess, basically for Natalie and Tim.
Yeah, I'll give you an example. And I haven't even really had time to chase it down and look at it yet. You've heard of the population of planets called hot Jupiters. These were the very first planet discoveries, like 51 Peg B, HD 209458b, which was the first transiting planet that was detected from the ground. These were all hot Jupiters. They're orbiting much closer to their star than Mercury is to our own sun. They're giant planets, so they really kind of turned everything upside down. We didn't expect giant planets to be orbiting so close to their stars. So there, you can envision that there might be an analogous hot Neptune population, kind of Neptune and Uranus-size objects that somehow got close in to their parent stars. And what we have found with Kepler is there really aren't. There's kind of a desert of planets around that what would be that hot Neptune population. And yet, among Tim's validated planet list, I think there's a very small number of things that have a very high likelihood of being a planet that are in that part of parameter space. So I'm really curious to go back and see and maybe try to initiate some follow-up observations to see if they are these kind of transient rogues that are passing through that part of parameter space, or if maybe we have their star properties wrong and then their planet properties wrong. Maybe they're slightly bigger or slightly smaller planets. So that'll be interesting to chase down in the years coming.
Yeah, and the thing that this kind of analysis enables is to sort of look at those corners of parameter space and see, are the 3 or 4 planets that we see in that part of radius period space, are those probably real planets or not, without doing the telescope observations first. So that's what this enables to do.
And a very quick follow-up. Is there anything here that changes or modifies, fine-tunes your understanding of, statistically speaking, the probability of or the distribution of habitable zone planets?
Well, we haven't done the calculations yet. So we've got these probabilities. We're going to repeat these calculations for the final catalog, and then we will really begin that work in earnest to understand the demographics of planets. So I don't know. I don't have really any more insight to offer at this point. Stay tuned for next year. I imagine in 2017, sometime before mission closeout, we'll be here again giving you an update on those statistics.
All right. Thank you.
Okay, we have time for one more question. We've got Margot Pierce from Extraordinary Limits.
Hello there. I saw a question from a group of fifth graders on Twitter that really strikes me as a fantastic question. What does this discovery mean for the future of science? Why should kids care about this?
That's a great question. What does this discovery mean for the future of science?
I can maybe comment on that.
Go ahead, Tim.
Natalie, I'm sure you have thoughts too, but just to kind of give a quick perspective. To me, what this represents is, that when you start studying something, you don't always know, not everything. Let me see if I can put this clearly. So when Natalie said when Kepler first started, we thought false positives were really common, but I came to start studying this problem with a completely fresh perspective, not having worked on this field for a long time, and was able to kind of have a clear vision to kind of see, ask the question, do we actually think that false positives will be common? And to me, that's kind of what this work represents, is that we're able to apply.
I don't think fifth graders are wondering if false positives are common.
That, in a kind of a fresh way, and see a kind of a paradigm shift with how we deal with transiting planets in this way. So that wasn't very clear. Maybe Natalie can take it too.
Well, I mean, my answers, of course, are going to be philosophical. I would say to the kids, we're going to change the way you see the universe. When you look up in the sky, you're not just going to see pinpoints of lights and see them as stars. You're going to see pinpoints of lights and see them as planetary systems. And it's part of that larger strategic goal of finding evidence of life beyond Earth, to know if we're alone or not, to know what kind of evolution, how life manifests itself in the galaxy, and what is the diversity, and being able to look up and point to a point of light and say that star has a living world orbiting it. I think that's very profound and speaks to, it answers questions about why we're here and how we got here. So for me, it's very kind of existential in that way, and I think even for the fifth graders, is evidenced by their question, I think. So that would be my answer.
Thank you for your time.
And that's what we've got for today's News Telecon. I'd like to thank the panelists and our operator for their time today. I'd like to ask the panelists to stay on the line for a few minutes for post follow-up. If you joined this telecon late, you can listen to it again by dialing 866-356.
Blah, blah, blah. All right. So there you have it. Not super exciting, but I thought I'd jump on live stream because I was going to sit here and check out the conference anyway. So basically, they announced 1,284 exoplanets, but I don't know if you can tell, but they're not entirely sure on the data. They keep saying, 99% positive that it's a planet, but then they're not sure if it's a bigger planet or a smaller planet, or, there's just not clarity there, which is interesting. But, all of this, I think, has to do with a greater agenda. I mean, we've talked about this all the time. Some of you guys in the chat room, which I was in and out of, you guys have been, discussing some of it, that, this is all kind of, I think, preparing us for something different, right? Something that's much more nefarious, and not to be like negative about the whole thing, but just it's obvious that they're peddling something. They've been pushing an agenda. There's been space propaganda for months, years, really. But, one of the things that I noticed this past weekend, and I'll maybe make another video about this, but basically the new movie that's coming out, Resurgence, with Independence Day. One of the things that's interesting about the 9/11 event is that the week 9/11 happened or the week after or something, I think there was a spike in rental of Independence Day because people somehow, the conditioning of that film reminded them of that, or reminded them of the event, or vice versa. There was something symbiotic there. So people went out and rented that movie to try to relate it to something they've seen in the movies. So I think it's interesting that this movie Resurgence is coming out, and not that Independence Day is the only film that does this. Obviously, tons of films do this and have been for a long time. But it could be telling that 20 years since it was 1996 when that movie came out, and then 2001 was the event. So here we are, 2016. They come out with Resurgence. Maybe between now and 2021, they're trying to plan something big. We know the 2030 agenda that you guys have seen videos on this channel and stuff. So in any case, I'm going to go make myself some lunch. Thank you guys for hanging out. I figured out how to block people and stuff, so I'm going to probably try to be more diligent in that regard. I haven't done this a lot, so I'm not entirely familiar with how everything works, but I can at least get it up and working, and just let me know. Give me some feedback. Love you guys. Thank you guys for watching and supporting the channel. That's it. Have an awesome day, guys. God bless.